Okay. Okay. Hi, everybody. Online, are you okay? Can you hear me? Can you give me a reply? Okay. I prefer you reply by voice because of the involved.
Yes, we can hear you.
Okay, good. So last time we stopped here with this example where we try to compute the inverse kinematics in closed form. You remember for a planar 2 degrees of freedom robot, and we started to say that we have some geometric intuition to apply. In particular, we were having as input data the position of the end effector, and we wanted to find out the values of the angles corresponding to that position. Now, one intuition we could have in this case is that the distance between the point P and the point O only depends on the angle Q2 and not on the angle Q1. So if we have it flat here, okay. Can I remove this?
Yeah.
How? Like this?
Just turn it around completely.
Okay. If we say the distance, we want to compute the distance and work out the value of Q2, we can compute the distance of the end effector with respect to the point O. And if we replace the above relationship, we find out that you have L1 C1 squared plus L2 C1 squared plus L1 squared S1 squared plus L2 S1 squared plus the term, mixed term C1 C2 S1 2, sorry, plus S1 S1 2. Now we can have a look better to this relationship, and we can find that there is something that can be simplified. In particular, if we collect these two terms, will be 1, and also these two terms will be the unity. So we can collect L1 squared plus L2 squared plus the mixed term, and we can recognize here the trigonometric identity for which this is equal to cosine of Q1 plus Q2 minus Q1. And this is equal to cosine of 2. So in essence, we have cosine of 2. We want to express this, and we put the other terms on the left. And divide by 2L1, L2. Again, remember, we try to resist to the temptation to do the arc cosine. So we compute the sine doing the square root of 1 minus cosine of 2 squared. And this is the sine of theta 2 of Q2 and the cosine of Q2. And again, with the arctan, we can compute the value of Q2. And we remember that arctangent function is defined in minus pi, so it's better than the arc cosine. And we have two solutions. Again, remember this, to the inverse kinematics, that are correspondent to the elbow up and elbow down configuration. Why? Because you can have, for example, a solution like this. This is the elbow down configuration, and a solution like this. And this is the elbow up configuration. And we see that in this case, this is Q2, the sine of Q2 is positive, while in this case, Q2 is negative, so the sine of Q2 is negative. Okay? Then the cosine of Q2 returns a value between -1 and 1. And this is a very good check. Remember to be sure that the end effector is inside the primary workspace. Because if we draw on the right the primary workspace or the reachable workspace, VS1, we remember that for a 2 degrees of freedom manipulator has this shape. And we will see that if we consider, for example, this inequality, this will be equal to px squared, py squared. And we put the lower than equal to L1, L2. We put this on the right, plus L1 squared plus L2 squared. And this is nothing else than L1 plus L2 squared. And this means that the end effector position should stay to be lower. The norm of the end effector position should be lower than equal the sum of the two links. So you remember was this this line here. We have the two links extended completely, L1, L2. Then the other inequality is that -1, so we put 2 L1, L2. We bring this on the left again, and we have, sorry, this is minus, we have plus L1 squared plus L2 squared, and this is a lower bound for the end effector norm of the position of the end effector. And this, again, if we look better at this, is L1 minus L2 squared. That is the exactly saying that the position of the position of the end effector should be bigger. The norm of the position of the end effector should be bigger than this, because this is the you remember the difference between the link length. Yeah, sorry, this is overlapping. Then what we do for Q1, we can again have another intuition, again geometric, and we can see Q1 as the difference between an angle like alpha and an angle beta. And again, for the angle alpha, we can, for example, compute it using the Atan-Chu of what? Yeah, the point in the vector. Atan-Chu, this is the angle alpha, so Atan-Chu of the Py component and the Px component. While for the angle beta, we can do something similar with this component that is, this is L2 and this is L1. How does this component look like? L2. Remember, we can use Q2 because we computed previously. So this is L2 sine of Q2. Perfect. We computed previously, so we have a number for that. And the cosine is what? This segment L1 is the length of link 1 plus L2 cosine of 2. Okay, and this will provide the value of Q1 as a function of these two angles that are come in our help. And we need to take care of the fact that this 2 will provide a value between minus pi and pi, but the sum of them might be not inside minus pi and pi, so you need to remap in minus pi the result. So if it's bigger than pi, you take into account the fact the angle, equivalent angle inside minus pi. And this is the elbow up, elbow down solution that we discuss. And another way we could use, another approach we could use to solve the inverse kinematic problem in this case is an algebraic approach. So we can find, for example, in the case of Q1, employ an algebraic method looking at the forward kinematic relationship. And if we look at them, we know that they are nonlinear in Q1 and Q2 because we have cosine and sine and so on. But if we consider as variable the cosine of Q1 and the sine of Q1 itself, because Q2 now is a number we computed before, so we know this number. But if we express in terms of cosine of Q1 and sine of Q1, the system is linear. And as a linear system, we know how to solve it. We can put in a matrix form, and we can call this matrix A. So we collect cosine of 1 and sine of 1. We call this matrix A, and these are our unknowns. And this is the known term that is our input for our inverse kinematic problem. And what we need to solve this, what we need to check to solve, to see if this system is solvable. Should be different than 0, bigger than 0 in this case. And because we need to compute the inverse of A to compute the value of X that are cosine and sine of theta 1, Q1, sorry. And when this determinant is 0, can you see that? This is always positive, this is always positive, this is always positive. Okay, that's okay, but it's not useful as an example of a robot because it's a robot with link length 0. But there is just one case. The cosine should be what? Which value should they have? K pi. Yeah. Oh, K pi is the angle. Yeah. So minus. This is the angle. The cosine is between -1 and 1. So which value should have? We can also have the change the link length. Huh? We didn't say that the link length should be different. So what if I set the link length equal and the Q2 equal to minus pi? You remember this is a singular configuration. You remember where you had that example where we were looking at the Dexter's workspace, where you could have the origin as a part of the Dexter's workspace, and you have infinite solutions. Remember of Q1 that correspond to the end effector. So in this particular situation where you're requiring an end effector to be in the origin, you have link lengths one equal to the other, you have a singular solution and you cannot solve this. So you cannot find your infinite solution for Q1, which makes sense in this situation. Otherwise, once you solved and you got C1 and so on, you can again do the trick of the Cartan-Chu with the value that you found. And you can find an example of this in the kinematic lab, a little bit more complex with degrees of freedom, but where we use the same concept. You need to solve a system linear equation to find the values of cosine and sine of Q1. Finally, summarizing what we found out in this case, in this exercise, we were able to find a closed analytic form in all the cases. We checked that we were in the reachable workspace in the first case and computed the two solutions that are the regular ones. So one solution for Q2 and one solution for Q1. We found out that for Q2 we have two solutions for Q1 and Q2. Two solutions for Q2 that corresponds to the fact that we have elbow up or elbow down configuration. This solution will collapse into one solution whenever the arm is completely extended. And we also computed the situation in which the only case where Q1 is not defined, that is the singularity. Now we can have a look to a more complex example of a robot that is a RPP. So rotational joint plus prismatic joint here and another prismatic joint here. And we want to compute the inverse kinematics for the position of the end effector. First, as we said, we need to compute the forward kinematics that I already provide you with these values. the prismatic joint. D3 is this, the extension of the prismatic joint, and the second prismatic joint by the extension of the first prismatic joint. D2 is here, and in here you have the effect of the rotational joint. So we want to have a look to these 4 kinematics. We know the position and orientation of the and the factor. They are our input data, and the orientation we can express as a rotation matrix in position as a geometric vector. And we compare with the expression, symbolic expression of our 4 kinematics, which is this one. And we can have a look to if we can find some intuition on solving this. How many are there? 3 times 3 plus 3, right? There are 12 nonlinear equations. So we can do this equal to this equal to this. So, but we see that we are writing 3 of them. We already have the information we need. For example, we can have a look that the value of the joint, prismatic joint, the second one, is equal, in this case, if we write this, to Pz. So we are ready. Our target is to find the value of theta 1, d2, and d3. And we already found out the value of d2, just having a look to this. Then, in the case of theta 1, we can see that we have a cosine and sine here. So again, in the case of theta 1, we can do the Altan-2 of what? Of our data entry of the rotational matrix R11. But there was a mistake here. First, we need to put the sign, right? And then the cosine. And we got this. So we got these 2. Now for D3, it's a little bit more involved. Do you have any idea? So did this one? Yeah. So what equation should I write? Yeah. And this should be equal. Hmm. So if we write this, py squared minus px squared, we have what? We have d3 squared c1 squared minus d3 squared s1 squared. Yeah. Okay. Cool. Then what we do? What we need to find the d3. d3 squared cosine sine squared, this is 1 equal to py squared minus bx squared. Okay. Yes. Minus bx because we have a minus here. Yeah. Yeah, it's correct. That was wrong. Because minus this is x squared is becoming like this, right? So we cannot collect, we cannot do the trick that we want to do. Like this. Okay. Then we can do that. Okay, I like. But yeah, we get two solutions because we have a square root. In alternative, we could, for example, do this px s1 plus py c1. You remember that we computed the theta 1 before, so these are numbers. And in this case, we know that this is s1 squared d3 plus c1 squared d3, and this is equal to d3. And we don't have to do the square root. Okay, but you found out a new way to do that. So that's exactly the point. You can use your intuition. You can find different way of doing things. Some of them have advantages. There is not really a strict rule. There is not really a procedure to follow. And that's exactly the difference between analytical and numerical method. So analytical method requires intuition, and analytical solution is preferable because you can code once forever and you forget, and it's very fast. You need to handle the situation where you have multiple solutions, and you need to code in your code. You need to discriminate with this multiple solution, elbow up and elbow down, something like that. You can use algebraic methods also to help you. And in very specific cases, for example, when you have 3 consecutive axes of revolute joint, or whenever you have a spherical wrist, this is a systematic way to reduce, to do whatever we did right now, to reduce the set of nonlinear equations to a very small number to be solved. Remember that the task function, instead in numerical methods, you start, they are mandatory if you have redundant robots, so number of degrees of freedom bigger than the dimension of the task. They are slower, but very easy to set up. You can use the same code to solve the inverse kinematics for whatever kind of manipulator, whatever number of degrees of freedom. And employ the analytic Jacobian. We will see now Octavio, I will introduce him. You already know him, but is today starting to teach you the part on differential kinematics. So on the mapping between joint velocities and end effector or task velocities. And using the analytic Jacobian, we see tomorrow we can use a Newton method or gradient method that helps in solving an optimization problem after many iteration of some iteration helps you allows you to converge to the solution of the inverse kinematics. Of course, this method is slower than the analytic one because you need to do iterations. But if there are no causal form solution available or not able to find them, is the only way you can do. So if you have questions about that, otherwise I give the space to Octavio. Good.
Okay, good. Yeah. Okay. Okay. Hello, everybody. Nice to meet you. It's nice to see some faces. So today I'm going to be teaching the lecture on direct differential kinematics. Today's lecture is a bit involved in notation, so I'm giving a bit of a recap on notation. Also, a bit of a recap on what we've seen in the previous lecture related to kinematics. So we started with direct kinematics, which is basically computing the pose of an n effector, in our case of what we're seeing of a manipulator, as a function of the joint variables in joint space. So it's basically doing this mapping. So we're going from the joint space on the right to the task space on the left. Okay. Then Professor Focchi just finished solving the problem for the inverse kinematics. And it's basically consists on going from the position variables, computing the position variables in terms of the n effector pose, which is a more interesting problem, right? Because you want to give a position in space, and then you want to know where would your joints be to reach that specific position, right? So it's basically doing the inverse mapping. So in this lecture, we're going to talk about direct differential kinematics. I'm saying direct because we're not computing the inverse problem today, because it's a bit more involved when you talk about velocities. So what direct differential kinematics means, and I'm putting this in parentheses because it's actually not a term well used in general in the community, but this is also, for example, Alessandro De Luca used it. So I like it because I'm only referring to the direct problem. So it's basically computing the motion of an n effector. So this means literally talking about velocities. So we say linear velocity, which is not completely correct. Like if you're being really formal, there's no such thing as a linear velocity, but there's only velocity, and then there's angular velocity. But we call it linear and angular because we want to separate between them, because we want to talk about these quantities. And we want to compute them as a function of the joint space velocities. But in the case of differential kinematics, we can do it in two different ways. So the first one is mapping from joint space to the task space, which is basically the task space is the variables of interest to us. So for example, in the last problem that Professor Focchi did, it was the position in X, the position in Y, the 2R, sorry, not the last one, but the 2R robot, which is the position in X, the position in Y, and the orientation of the end effector. And we can obtain this by just working on the differentiation of the direct kinematics. So basically differentiating the direct kinematics function in terms of the joint space variables, which is do you see my cursor? Yes. The partial derivative that you see here in the middle. And then I have another equality on the right. And this is what the professor said before, which is the analytical Jacobian, which is a key concept to do, for example, numerical inverse kinematics, and a lot of topics in the future that we're going to be deriving today. And the other mapping that we can do, it's instead of just talking about the task space, we want to talk about the Cartesian workspace, which is basically the velocities and the in linear and angular, both of them. And these are represented by a vector of 6 dimension. The top 3 elements are the linear velocities, the bottom 3 elements are the angular velocities. And this is related to working directly at the differential level. So you need to get more intuition about the geometry of your actuator to actually derive these expressions. And this is related to what we're going to call the geometric Jacobian. And this is what we're going to start with today. Well, not today, but we're going to do first the geometric Jacobian and then the analytical Jacobian. So as I said, let's do a bit of a recap on notation. So I have very bad handwriting. So I did my slides using LaTeX. So I'm going to do a bit of a recap, and so you don't get lost in all the variables. So first of all, lowercase non-bold letters are scalars. So here you have A and B, lowercase non-bold. Then lowercase bold letters we refer to vectors, and uppercase bold letters are matrices. It's important to say that this does not apply to not only subindices but also subparentheses or all indices. It's not applied because sometimes you can be referring to a point, you can be referring to a frame when we use uppercase letters. Then a bit of a recap on the previous lectures on kinematics. So if we have an expression like the one on the left on the slide, we're gonna be we need to read this as it's on the slide. The position vector representing point B expressed in frame A, right? So this frame, which origin it's this OA, it's basically this vector here. Okay. Then we have an alternative way of doing this. Let's say we have 2 points in the Cartesian space. So we can read this vector as the position vector pointing from B to C expressed in frame A. It's important always to keep in mind that we always want to say in which frame we're expressing things, because you can only add things up in the same frame. And there's also this alternative notation, which it's going to be very I'm going to be using a lot today, because we're going to be moving from consecutive frames in a kinematic chain, and we add this comma here because then it becomes really difficult to read if you don't separate between the eyes. So this basically reads as the position vector pointing from I to I plus expressed in the frame of I. It's just for if you see this notation, don't be surprised. And then the classical, just to give all the notations that I'm going to be using. This is the rotation matrix from frame A to frame B. Okay. So let's start. We're going to start simple with the kinematic analysis of a point with a moving frame. Okay. So let's start with the fact that we have a frame A, which is fixed in space. This is not moving. And then we have a frame B, which is moving, which can be represented by this vector pointing from the origin of frame A to the origin of frame B. And this frame is moving with a velocity which can be obtained by the derivative of this vector, the time derivative of this vector. And it's moving also with an angular velocity, which is represented by omega expressed in frame A. Okay. Now we have a point C, yet not assigned to any frame. And this point C, it's represented by this vector, which is BC. Now I'm putting a star there. This is a star, because this vector can be both represented seen from frame A or frame B, but it's the same vector. So we can describe this using this expression. So this is the vector that we care, which is the vector pointing from the origin of frame A to point C, which is this. And then you have the vector representing the pointing from the origin of frame A to the origin of frame B, plus the vector that is from the origin of frame B to the point. And this is just all expressed in frame A, so we can add easily. And we can obtain the velocity of this vector if we take the time derivative with respect to time, which is basically this. So this is the time derivative, then the time derivative of this vector. We're just putting a dot on top of the moving of the vector. And then for now, I'm just keeping express this because we're going to derive it in a different way. We're going to the third term, the rightmost term, it's only expressed. So in the next slide, I'm going to work it in a different way so that we can get a bit of more of an intuition on how a point behaves when it's moving with respect to a moving frame. So this is again our expression for the point C expressed all in A, but let's rewrite it in a different way. So what I'm doing here, I'm only expressing the vector with respect to frame B first. But of course, if we need to add them, we need to add a rotation matrix. So pre-multiply the vector by a rotation matrix to have everything expressed in the same frame. Okay. Then we can take the time derivative of this, and the first term remains the same. But then, of course, we have a multiplication of two variables depending on time. So then this you need to do the rule of you keep one constant, you take the derivative of the second one, and so on and so forth, and the chain rule. And this becomes this. So let's look at each term one by one. So of course, the first one is the velocity of point C seen by frame A. This one, it's the velocity of the frame B seen by the frame A. This second term is the variation due to the motion of C with respect to the frame B. So it's the motion of this point related to the point C related to the origin of frame B. And the third one, it's the variation due to the rotation of the frame B. Okay, so as the frame moves, this also generates a motion in Z. And what's important to note is that these two terms that are highlighted with the green squares are due to the motion of the frame B. Okay, so let's keep our heads on them. But what happens in the case of a rigid body, which is what we care about, because all links in at least we are assuming that all of our links are rigid. So let's have again our diagram here, but now let's consider that C and frame B are contained within a rigid body. Okay, so what is the difference here is that C and the origin of B they don't have any relative motion because they are subject to rigidity constraints, and that of course they're rigidly attached to each other. So let's rewrite the expression that we had from the derivative taken from expression 2, and this is just copying from the previous slide. But what's important to note here is that this term here, because there's no change there's no relative motion between these two, this will become 0. So this term goes away. And now keep in mind this expression, because this is the derivative, because in the next expression, this is the derivative of the rotation matrix, which is, I'm going to replace this derivative with this expression. If you want to go back, you can always look at the slides. So when I'm always referring to expressions in previous lectures, I'm always putting the number of slides. So when you're studying, you can just refer back to the slide. So here we have the expression removing the term in the middle, and then we are replacing the derivative of the rotation matrix by the expression on the right. And in the end, this we come back to the previous expression that we had, which is expressing the vector that goes from the origin of B to point C with respect to A. And then this is the velocity of the body, of the rigid body. So it's a very compact expression that comes also from the fact that we are assuming rigidity constraints. Now, just also, I'm going to talk about a bit of angular velocity. So consider these two examples, these poorly drawn examples, where you have, let's say, a 2-degree of freedom arm. So the first one is extended, but they're both rotating with the same angular velocity. Okay, and then at the end of this arm, you have a frame, right, pointing both in the same direction at the very beginning. So this is rotating with an angular velocity. At this example, is 2 pi radians, so it's a full rotation. So when you do the full rotation, you're going to be actually coming back to the same orientation, right? And they are become. Yeah, but like I cannot show it to the camera, but that's fine. So like it's gonna if you do a full rotation, let's say if I'm going out of the
rotation, what which axis is?
About the z-axis pointing outwards from the slide. So if the axis is pointing outwards of the slide, and this is the frame, let's say my hand is going out of the camera now, and it's going to do a full rotation outside of camera, and then it's going to come back and it's going to have the same rotation, right? So this means that the rate of change in the angular rotation, it's the same because the orientation of this angle is going to be the same. And this is exactly what I'm saying. After 1 second, this is going to come back to the same point, okay? Now, if we translate this to a rigid body, you have two frames located at two different points. When you do a full rotation, those two frames are going to be pointing in the same direction when if you do a rotation at the same time. So what I'm trying to say here, this simple explanation, is just to say that the angular velocity is the same for the entire rigid body. So we don't have to care about like having different velocities along the rigid body. Okay, so now that we define the velocity of a rigid body for a body.
The linear one depends on the.
Yes, okay. So the linear one also depends on the point because you have the expression. I'm going to write it here. Hopefully I can write it. When you talk about the linear velocity, you have the velocity times omega cross r. And of course, r here is different to r here, right? So this velocity is going to be different for each point. And it also applies in the case where you're stretching and collapsing the arm. Okay, good. So now let's talk about the velocity of a rigid body, but now related to a rigid body in a manipulator, which is basically a link. So there are two sets of differential quantities that we care about. So the first one that I would like to talk about is the linear and the angular velocities of the n effector, which are these two vectors right there. This is a v, because I have very handwriting, so people can be confused with an n. So these two quantities, what's important to know about these two quantities is that these are members of a vector space. So they satisfy a number of axioms, which are distributivity, associativity, and so on and so forth. But what's most important for us is that you can actually add them. So you can add the contributions of each of the joints in a kinematic chain. So for example, you can add the angular velocity of joint 1, the angular velocity of joint 2, the linear velocity, and then you can obtain the sum and relate it to the n effector velocity. This is key for the things that we're going to be working today, because we're going to start from the beginning of the kinematic chain to the end of the kinematic chain. Okay. Now, the other rotational quantity that we are interested about, it's the rotational rate of the n effector. What I mean by this is related to the angles representing the sequence of rotations corresponding to a minima representation. So, for example, Euler angles, as the professor showed in previous lectures. And what we care is that it's a rate of change of this. What's important, and this is like key to keep in mind, is that this is not a member of a vector space. So you cannot add, let's say, the yaw rate of one vector with the yaw rate of one joint with the yaw rate of the next one, and get the yaw rate at the yaw rate at the other vector. And this is what I'm trying to say here. So in general, these two are different, and only under very specific circumstances where the frames are coincidental, but this is generally not the case. And it's always good to keep in mind that these are always different. So what we're going to do, as I mentioned, is that we're going to find expressions for the linear. Now I'm referring here as vi plus 1, because we're going to do it with respect to their predecessor link, right? So we're going to find expressions of the linear velocity and the angular velocity with respect to their previous links, as I mentioned, because what we have certainty is that the base link, it's not moving, and then from there on we can have a certainty as we move on the kinematic chain. So once we compute this function with respect to the previous link, what we only need to know is the direct kinematics of the full chain. So as a recap on frames, because I'm going to be referring a bit of to frames in the upcoming slides. So this is a slide taken from the previous lectures. Here, what's important to know is that the joint frame. So for example, let's look at joint frame I+1. It's supporting link I+1. In the case of so the link frame, which is the one in red, it's moving, and joint I+1 remains fixed with respect to that specific link. So that's what we're going to measure that's what we're going to use to measure the joint variables. And this also can be we also apply this convention to prismatic joints. So joint I+1 supports link I+1. And I'm making this small recap because of two things. One is that I'm going to be basing this on, based on this for the next slides, but also this is different to the book that we put as a reference, because in the book that we use as a reference, they use link, the predecessor link to support the next one. And this was a bit less intuitive for us. And for the derivations, it's easier for us to use, having the joint frame supporting the link frame with the same index. Okay.
Also because in the simulation, in the lab, we prepare.
Also because
with ROS, the convention is commonly used. It's this one, so we have better expression, more intuitive, and for the libraries that you can find.
Yeah, everything is expressed with as when we're starting the lectures, we said that we're not going to use Hartenberg. We're going to use URDF. So all of this URDF is expressed with this frame convention. Yeah, URDF stands for Unified Robot Description File, just because I think we've never mentioned it explicitly. So let's consider an arbitrary link I, which is from a kinematic chain. We have the other links of the chain in gray attached to the joints. And this link is attached to joint I and I+1. And we also defined a world frame, which in the previous slides I was referring as frame A. Now the world frame, it's a fixed frame, also called an inertial frame because it's not subject to any acceleration. And we can express the points connecting to the joint frames by these two vectors, which is the vector P expressed in the world pointing to I, and vector P expressed in the world pointing to I+1. And we can express the position of joint I+1 in terms of joint I. So namely its predecessor, as I mentioned, we're going to go from the first to the last one in the world frame according to this expression. Now let's go, let's talk about this expression term by term. So this is what we want, the position of joint. So basically we want to find this vector that expresses the position of frame I+1. So we have the position of frame I expressed by the vector, this gray vector here that points to the frame I, the blue frame. And of course we can add the points to get the next one. But in order to get that, we have this other vector here that I'm going to explain, which is a vector that connects joint I and joint I+1. Okay, but of course this vector now it's expressed with respect to I, so we need to add a transformation matrix before, so we need to multiply so that everything is expressed with respect to the same thing. Okay, so now that we have this, we can differentiate with respect to time to get the velocity, and we get this expression here. So the first one is just basically taking the time derivative of the position of the position vector that points to link I. Then the second one, as I mentioned, we have the chain rule, and we get this first expression. We keep the rotation matrix constant. We take the derivative of the point, and then in this one, I'm just replacing R dot with the expression of omega cross R. which is this one. And again, I'm reminding you this omega cross r, which is the derivative of the expression of the derivative of a rotation matrix. Okay, so here I'm just writing down again the same expression that we just derived. If I'm going too fast, if you're copying and you feel like I'm going too fast, just let me know so I can slow down.
Also, if you have any questions.
If you have any questions, you can always stop me. Okay, good. See, because I saw you writing and I thought maybe.
Maybe go back once. From vector, the vector from link I would say, not they are constant in the link frame moves with the link, and the origin is constant with the joint, the supporting joint. But I would say this is from link I to link
yes. Yes.
Because between link I and link I plus 1, there is the joint in the middle. Okay.
Yeah.
That will create. We create a motion, so we create this vector you're talking about.
Yes.
So this is just
yeah. It's because we're referring to link frames, not joint frames. Okay. So let's go back with the same expression. Let's stay with the same expression. So let's go term by term. So this basically it's the derivative of a position vector is the velocity. So we are interested in velocities. So this is easy. It's just the velocity of I plus 1. Then this is the velocity of point of I. Then this expression is basically just applying a rotation matrix to the vector of velocity expressed in frame I, which takes us to the velocity from joint I to joint I plus 1 expressed in the world frame. And this one as well, very similarly, but this is for position, it's the position from link I to link I plus 1 expressed in the world frame, because we are pre-multiplying by the rotation matrix. Okay? So we get to this expression if we replace what we saw in the previous step, and we can get the linear velocity of link I plus 1 as a function of the linear and angular velocities of link I, which is the objective that we have today. Okay, so we get this compact expression still. Now let's go to the angular velocity, and for the angular velocity, let's keep the same length. And it's good to start the analysis from the expression of the composition of rotation matrices. So if we want to get the rotation matrix of link I plus 1, then we can just get the rotation matrix of the predecessor link, which is the one on the left of the right hand side of the equation, multiplied by the rotation matrix, the composite rotation matrix from I to I plus 1. Since we're interested in velocities, then we take the time derivative of this expression, and then by the chain rule, we get these two terms here. And please recall again the derivative of the rotation matrix, but also this expression. This is basically the same as on top, it should be on the same line. But it's basically that omega cross R can be expressed also as the skew symmetric matrix of omega times the rotation matrix. So remember that the cross product can be expressed as a skew symmetric matrix. And if we replace this, if we replace these two expressions on the expression on top, we get that the time derivative of the first term, which is a skew symmetric matrix of omega multiplied by vector R by the rotation matrix of I plus 1, it's equal to the skew symmetric matrix of omega multiplied so we're replacing the first rotation matrix, and by the skew symmetric matrix times the rotation matrix, and multiplied by R by the rotation matrix expressed in from I to I plus 1. And then the last term Again, we're replacing the derivative of the rotation matrix by the skew symmetric matrix times the rotation matrix itself. Okay, is this clear? Yeah. Yes, so the skew symmetric matrix is like this. So you have on the diagonal, you have this, then you have minus omega x, omega y, minus omega z.
Yeah, double check. I'm not sure.
Yeah.
Maybe omega z is in the second.
Yeah, let me double check that because can you check on the slide just so I don't get this wrong. I think that all right.
No, this is a rotation matrix. Sorry, it's 3 times 3 matrix. Sorry, not a rotation. It's a 3 times 3 matrix associated to the cross product. Nothing to do with
so
the.
Maybe I need to write it down on the slide.
Transforms. Yes. Yeah, but you can find it. It's always because it's a minus or plus sign, and it's always difficult to remember. But
you have the slides printed there? Did you just
these ones.
Okay, let me just check it back.
Yeah, the component is the second one.
Let me just check, just to be sure.
Yeah.
Is it?
Yeah. Yes. Level 2.
Okay. No, I had. Yes, you're there with you. Okay, good. Good that we checked. So let me go back to presentation mode. We were here. So this is. I'm gonna just show omega here, without just to make it less notationally heavy. So 0, 0, 0. Then here you have minus omega z, omega y, minus omega x. And then here you have omega z minus omega y and omega x. Oh, wait. Yes. Yeah.
Because of the anti-symmetry property.
Yes. Sorry, but this is not very aligned. Let me just write it a bit nicer. This is here. Okay, it's like this. So you remember now? It's and this is equivalent to omega cross, which is what I'm replacing it for here. So this is what S of omega replaces. Okay. Any other question? Yeah. Yes.
I to y plus 1 from I plus 1.
Yes. If you let me show you the previous slide. So we're talking about linked frames. So there's the joint frame, which is the purple one here, or blue.
It's blue.
I'm colorblind, so and then this is and then there's also the link frame. Okay, so if we're talking about, for example, rotation revolute joints, then you see that the frame of link I, the orientation is coincidental with the frame of joint I. So this is going to give us but now we're talking about relations between links. So it's from link I to link I plus 1.
In the middle, there is joint I.
Yes. I see you still.
I would say between link I to joint I plus 1.
Yes.
Then with the rotation. So
Yeah, we
that affects the rotation part, but think about the prismatic joint.
So what we're talking about, what we're talking about is the relation between two links. I mean, you're right, because the link, the actual joint variable is measured with respect to the joint frame. Okay, but what we're gonna get in the end, it's the differential between the predecessor link and the next link. Okay, but in this case, link I and joint I plus 1 are coincident in terms of orientation. For example, if you're talking about the revolute joint. Okay.
you want to obtain link I plus one.
Yes.
But the sentence would be link I to join.
No, because
we're just talking about relationships between links. Okay. So it's from one link to another link. In this case, although I think maybe your confusion comes from the fact that the link and the joint frame are not coincidental in the origin, but we're just talking about the orientation of the link. We're not talking about the position of the frame. Well, we're talking about the orientation of the frame, not about the specific position.
the joint I plus one moves with link I frame. They are just rigid transform. Remember that. Then
Okay.
you can have either a prismatic joint or a rotational joint. Move link plus one with link.
How are we doing with time?
38. In 10 minutes, I will do the break.
Okay, just let me know.
Yeah.
Okay, we were here. Okay, any other question? Okay, good. Also from the chat, actually I can do this. Okay. If there are questions from the chat, you can write it down and I'm looking at them right now. Okay, now, so I'm going to write down the last expression that we have in this slide on top of this one. Yes? Of course, you're right.
There is a reason for which I tell to ask.
Yeah.
But
Then open your mic.
self-
Open your mic if you have a question. Okay. Now we have the expression of the bottom of the slide, which now we're using skew symmetric matrix. This looks more heavy, but then you'll see that there's a reason for this. So let's start with this. Let's start simplifying this expression. So in the end, we have the rotation matrix from the wall frame to joint I, and then we have just the composition of matrices from the predecessor joint to the next one. So in the end, this becomes just the rotation matrix from the wall frame to the next to joint I plus one. So let's put it back as we reduced it now, and let's take a look at this term on the right here and see if we can simplify it a bit. Okay. So again, I'm putting that A here, it's equal to the same term on top. And then we do a small mathematical trick, which is basically multiplying by identity. And this is basically saying multiplying R times R transpose. And what's this, the help that this gives us is that this on this side becomes the rotation matrix from the wall frame to I plus one. And on this side, we get this expression. Now, let me point you to this property on the right, which is basically if you have R transpose, so if you have a skew symmetric matrix multiply of an omega vector multiplied in between R and R transpose, you can actually put R inside of the skew symmetric operator that we're using here, and it's basically equivalent as transforming the inside vector with respect to the frame of the vector inside of the skew symmetric operator. So that's what we're doing here on the red. That's indicated in red. Basically, we're using this property to just put inside of the skew symmetric operator the rotation matrix. Okay, was this clear? Do you want me to go like write it down somewhere? No questions. Okay. So then we have the expression now with the simplified version of the term that I'm calling A. So let's put this back again here, and we're gonna do a small trick, which is post multiplying by this matrix here, which is the transpose of the rotation matrix from wall to I from link I plus one. Then what we're gonna have here, which is very interesting, is that all of this, they become identity because we're having R times R transpose, which is identity. And also what we're going to be getting, it's that we can also reduce this. Well, this is not related to the post multiplication, but let's further simplify this because this is expressing the angular velocity from I to I plus 1 in terms of the world frame. That's why we have the pre-multiplication of the rotation matrix there. And if we use all of these simplifications, what we end up with is this very compact expression in terms of the skew symmetric matrix. And now, because as we showed before, we have the expression of the skew symmetric matrix. This is omega z, omega 1, then omega z minus omega 1, 0, minus omega x, 0. We can actually, because we're using the same operator in all three terms, we can actually just say this, that the angular velocity of link I plus 1, it's equal to the angular velocity of the predecessor link plus the angular velocity from the predecessor link, which is I to I plus 1. Is this clear? Any questions? Okay, so let's continue. Again, this is just saying the angular velocity of link I plus 1. This is as a function of the predecessor link, which is I. So we end up with these two expressions, one for the linear velocity and one for the angular velocity. Now let's look at each of this, of the elements of these expressions on the right-hand side of the equations. So as I mentioned, all that has the subindex I, it's with respect to the predecessor link. So in theory, if we go from 0 to whatever frame we are, to whatever link we are, we should know this. Because we are going from the very bottom, which is the base link, and this is the only one which we have certainty, and then we go to the top.
If you're okay, we can do a break here. What do you think?
Let me finish this slide, and then we do the break. Then this, it's obtained directly from the direct kinematics, which we already know. We're assuming that we know the direct kinematics. And we end up with these two terms here, which are the most important ones that we're going to be working with in the next slides. And this, it's basically telling us what is the change of velocity from the predecessor link to the one that we care about. And this depend on the type of joint. In our case, because we're looking at manipulators, this depends on the type of joint that we're looking at. And as I mentioned, we're going to be using the expressions from the beginning of the kinematic chain, which is the base link, to the end of the kinematic chain, which is the end effector. And they depend on the type of joint that we have. And if we want, we can do the break here. If you have any questions, you can come to me now, or you can write them in the chat and I'll take a look. Okay? Good. So let's have our break.
So okay, can everybody hear me? Sorry, can anybody hear me?
Yes. Yes.
Okay, so I do a quick announcement on the exam. Me and Octavio were thinking about how to structure it, and we will do an announcement soon on where we define for each argument of the course how high is the probability that will be some question in that topic. So there are some, this course, as you notice, is full of is very thick, is very full of information. So we cannot ask everything in detail. There are some topics that are more important, and the other ones are just to give you a broad introduction for the next years. If you decide to continue in a robotic path, if you decide to do other courses in robotics. So this is this information, in our opinion, are important, are what you need to have pointers to start understanding all the topics you need in robotics. So on the same time, we understand that for a 6-credit course is a lot of information. So we will detail for each topic if we will do some open questions or there will be an exercise on that topic or not, and what is the importance of that topic. Let's say from 0 to 5, where 5 is the hottest topic that you should study in detail, and 0.5 is something just very, or 0 is something we don't ask at all. For example, we don't put in, we don't give any questions at all. So this is just something I want to say, because somebody of you during the questionnaire were asking for about defining better the rules of the exam. And you should have found that the first one is on the 7th of June. So it's quite close. By the end of the course, you will have only 2 weeks. So we will also try to be a little bit more less strict in that date, let's say. Okay, I let you continue.
Okay. Just one question. Is the audio better now? For those online?
Yes.
Okay.
Very good.
Okay, thanks. Okay, let's put this back to full screen. How can I do this?
Let's double click.
Okay, good. Any question regarding what we've seen so far? Nothing that you thought about during the break? Good. Let me put on back my glasses. Okay. Now, okay, good. So now let's talk about it. Let's talk about the velocity of a rigid body, link of a manipulator, but now specifically we're going to start with the prismatic joint. Okay. So consider link I+1 indicated by the frame in green in the slide, supported by joint I+1. Remember that the supporting that the joint I+1 is the one that supports the link, and the motion is given along this the axis of the joint I+1. Now we have another joint, which is the predecessor joint, which is the predecessor link, which is link I, supported by joint I. And there you see that the difference in motion is given. It's given because there's the rotation of the. Here, this one is a revolute joint, for example.
Yeah.
Now the link I is revolute.
Sorry.
Link I is revolute. Link I+1 it's prismatic. So the angular velocity of link I+1 with respect to link I is given by, any guess? So what is the velocity, the angular velocity of link I plus 1 with respect to link I? Good, easy question. So the angular velocity of that is because this is a prismatic joint. So this becomes 0. And because there is no change in orientation from I to I plus 1. And the linear velocity of link I plus 1 with respect to link I is, do you have any guess for this one? Okay. It's just this, which is the displacement given along the axis of joint I plus 1, which is the I plus 1. It's better written here. And then we take the time derivative of this because these variables, remember, that are time dependent. These are our joint variables. And this is and this is the linear velocity given from link I to link I plus 1. What's important to note is that this set I plus 1, it's the axis of motion. So where is this set I plus 1 in the drawing? It's here, it's this axis like this. And this is the convention that we're using. Like, you can do whatever you want, but it's better to follow a convention because everybody else does it. And then if you want to collaborate with someone, you want to use a specific software, they're using specific conventions. So the axis of motion, it's the one along it's the set axis of the joint axis. And it's called the line of action along joint I plus 1. Okay. And both the expressions of linear and angular velocity, according to the previous slide, if we replace these two, then we have the velocity from I to I plus 1 given by the expression here, and the angular velocity, and the linear velocity just given by the with respect to its predecessor link, and the position with the direct kinematics. This is the same as it was in the slide before. And then the angular velocity is just the angular velocity of the previous link, and that's it, because the second term of the right hand side of the equation becomes 0. And I put a square here because these are important. Okay, now let's talk about the revolute joint. Now we have this manipulator, which is only made of revolute joints. And then we consider link I plus 1 supported by joint I plus 1, as we did in the previous case. Then we also have a link I supported by joint I. And the angular velocity of this link, it's given by the rotation, the derivative of the joint variable, which in this case is theta of I plus 1, along the axis of rotation of joint I plus 1. And this axis of rotation is the set coming out of the slide. And let me show you where that is. It's this small point. Usually when you talk about 3 dimensions, I think this is very well known. When you have a vector pointing out of the page or pointing out of the slide, you use a point here. Here's the point. This is I hope this is purple point. If I remove it, there's the purple point when you put, and when you put it pointing towards the slide, you put a cross. It's like an arrow, basically. Okay, so again, this is the axis of rotation acting on joint I plus 1. And this is also detailed in previous lectures. And then we have the linear velocity of link I plus 1 with respect to link I is given by this expression, which is basically the expression that I showed you about the linear velocity of a point along an axis. So it's basically omega cross r that I showed you in the first 2 slides. And in this axis, it's basically the position vector from I to I plus 1. And remember that we have to express everything with respect to the world. So this is the angular velocity of joint I cross the position vector from joint I to joint I plus 1. So both of the expressions that we showed in the 2 slides ago, they become, if we use this expression for I to I plus 1, the linear velocity of link I plus 1 becomes the velocity of the predecessor link plus the cross product between the angular velocity of the link I plus 1. Of course, we still don't know this, and the position vector from link I from link I to link I plus 1. But I told you that we didn't know this omega cross I, but then we can get it as well. I'm just put them the other way, the other one, just to keep the order as in the previous slide. So here you have omega I plus 1. It's equal to the angular velocity of the predecessor link plus the derivative of the joint variable that in this case it's I theta I plus 1 times the axis of rotation of joint I plus 1. And these are our expressions for the revolute joint, for the linear and angular velocities of the revolute joint. Any questions so far? No, that's I plus 1. Tell me.
Can you repeat the definition of omega I comma I plus 1 and the difference between that and the omega I plus 1?
Yeah, so you're asking the difference between omega I plus 1, like, and
Omega I plus 1.
Ah, okay, yes. So it all comes back to the frame. Okay. So if we have 2 frames here, and then you have I don't have another color and I don't want it. So let's call this our world frame, right? So omega I comma I plus 1, it's the angular velocity of from link I to link I plus 1, whereas so it's just the angular. So let me show you something here. I think I have a drawing where it's shown more clearly. Okay, let's look at this on top. Okay, so this is link I plus 1 and this is link I. Okay, so from link and if we have a world frame here, okay, this link I plus 1 has an angular velocity related to all of the previous links on the kinematic chain. So if you add a link here, let's say, the velocity, so this velocity I plus 1, sorry, it's horrible. Let me write it here. So the velocity I plus 1 would also consider the velocity of this, the angular velocity of this link. So remember that we can add along the kinematic chain the velocities. So this would be the velocity due to omega 0, omega 1, omega 2, omega 3. Now the velocity I comma I plus 1 expressed in the world frame is just the velocity between link I and link I plus 1. So it's just the contribution of that specific joint to the overall angular velocity.
But I open up parentheses. You're right. The notation is not so clear because we should express also in the case with the first term I plus 1, we assume that the starting frame is the world frame, and whatever frame is on the right side of omega is the frame we want to express the angular velocity with respect to the world frame. But we should also, in the case of the world frame, define the frame from which we are referring about which we are referring the angular velocity. So we don't do that just to not make the notation very heavy. We just do in the case of I plus 1 to show the relative rotation of one link with respect to the other. But the notation is not so clear. While, because remember on the left subscript, you just express the frame in which you are expressing this vector that represents the angular velocity. But the angular velocity is always between two frames. So, but we assume that when we don't write anything, we just write one subscript is because the starting one.
Okay, I understand what you're saying. So what you're saying is we should write,
yeah,
like this.
Yeah, but this, I mean,
then it's already a bit notationally heavy, so we don't want to make it. So whenever you only see one superscript on the right, one subscript on the right hand side, it's with respect to the world. Okay. And it's important to understand this difference. It's good that you asked the question, because when we talk about the Jacobian, this is the most important term, because this is actually what tells us the contribution of each specific joint to the final end effector velocity. The rest we just know from the previous joints. Okay. So we finished this one. Okay. Let's see if there are any questions. No. Okay. So let's continue. So as I mentioned, the previous expressions, they're going to help us to compute the velocity of any rigid body with respect to the predecessor of both prismatic and revolute joints. So now let's group these joints as a column vector, these joint variables as a column vector. So for example, here I'm just putting examples. In general, how we do actually, it's that we have Q equal Q1, Q2, Qn, right? But here I'm putting thetas and these, because this means that in this vector, we're going to put both revolute and prismatic joint variables. And the goal that we have is that we want to describe the linear velocity of the n effector, always denoted by the e, and the angular velocity of the n effector as a function of the joint positions and the joint velocities. So this q vector and its derivative. And in the end, what we want to have is an expression like this. So we have the velocity of the n effector expressed actually as the sum of the velocities of all of the joints along the kinematic chain. And the form that this expression will take, it's a matrix J as a function of the joint velocity multiplied, as a function of the joint position multiplied by the joint velocities. And the matrix J is usually referred as the geometric Jacobian or manipulator Jacobian. Okay, so the geometric Jacobian can also be decomposed in two parts, one corresponding to the linear part and one corresponding to the angular linear contribution and the angular contribution of the velocities. I don't know why in the Chilenos book they use P and O to talk about the linear contribution. I guess it's related to the type of joint, which is prismatic and orientation, but position and orientation. But I because it's their velocities, so I would prefer it to be called, but then I'm just using the notation that they have there. So we have the Jacobian of the linear part on top and the Jacobian on the angular part on bottom, or sorry, in the bottom. And this both JP and JO are comprised by the contributions of the linear and angular velocity. So these are the result of a sum of contributions of each of the joint variables along the kinematic chain. So it is convenient to compute both so the linear contribution to the Jacobian and the angular contribution to the Jacobian, depending on the type of joint that we're dealing with. So it could be prismatic or it could be revolute. We're doing it like this because of the rigid body constraints, because we're dealing with manipulators. So we can write the velocity at the n effector by obtaining the derivative of the position using the chain rule. Is this expression clear? It's just taking the derivative of the position of the n effector, which is obtained by the chain rule, which is basically the derivative of time of the joint variable, and then you're gonna have something like sorry, dq dt, and then if we remove the summation for now, it would be dpe over dqi. So by the chain rule, we can, I mean, doing a bit of abuse of notation, we can say that this is this, and we basically get back this. And it's a summation because we're going to do it along the kinematic chain. So we're talking about the velocity of the n effector. Okay, let me get rid of this. Okay, so
the out of the columns.
yes, I think I have it here. No, and this JPI is actually the columns of the Jacobian. If we go here, and the dimension of these columns is 6. So it's a 6-dimensional vector, because it corresponds to the Cartesian workspace variables. Okay. Let me get rid of this. Okay, so we need to compute the linear velocity of joint I+1 to the origin of the frame attached to the n effector frame. And there are two possible cases to do this. One, if the joint is prismatic or revolute. So in the case of a prismatic, it's gonna look something like this. So this is a full kinematic chain, and we're paying attention to the prismatic joint that it's indicated here by qi+1, and then the dashed lines indicate that the kinematic there are links in between these two. And the second case is a revolute joint. And this is the case where the joint variable it's an angle, and again the dashed lines, they indicate that there are elements in between the links of the kinematic chain. Okay, so let's start with the prismatic joint. So in the case of a prismatic joint, what we're gonna do is that we're gonna assume that all the links after the joint that we're looking at, they're frozen. What do I mean by this is that basically the velocity of the n effector after this point, this is the point that we're analyzing, it's just equal to the velocity of the specific contribution of that joint. So as we were trying to explain, it's just the velocity from I to I+1. All the rest is frozen, it's not moving. So with this in mind, we can say that we can just take from the expression that we learned before that the velocity from joint link I to link I+1 is just given by the displacement of the prismatic joint, which is the derivative of the joint space variable d multiplied by the line of action of the joint of the joint frame. This is in slide 21, in case you want to go to the slide. And then I'm just saying here that the I+1 is the joint space coordinate of the manipulator, and they are usually referred as Q. And this leads to these two expressions. So if we equate that this is our joint space variable, and then we want to obtain this expression that it's related to the Jacobian, remember that our summation is something like J pi times qi dot, but this is a scalar, so we can take it out, we can move it wherever we want. So that's why here I'm putting it on the left hand side. And just to say that this qi+1, it's actually equal to the I+1, and basically what we end up with is that our Jacobian is basically the vector representing the axis of motion. I'm going to do an example with a 2R robot, and this is going to be a bit clearer what CI plus 1 look like. This is basically, let's say if we have a 2-dimensional robot, our set vector is going to be something like this. So in the case of a prismatic joint, the Jacobian is constant. Then we'll see that for revolute joint, this is not the case. So let me just get rid of this, just so that we have clean slides. And this as well. Okay. Now, in the case of the linear contribution on a revolute joint, what we want to do is actually compute directly with reference to the origin of the n effector. So what do I mean by this? I'm just going to show the expression, but then I'm going to explain each of the terms of the expression just to be a bit clearer. So let's start with this is in slide 22, and let's start with this one. This basically it's the position vector from the joint that we care, which is I plus 1, to the n effector, right? So it's just this vector that goes from the joint that we're analyzing to the n effector, and where, as I said, we're going to compute the linear velocity due to the rotational motion. So it's basically just doing omega cross r, where r it's just the position vector that connects these two joints, right? So this is what we're seeing here, omega cross r. And then we can also express actually this vector as the difference between these two vectors, which is the vector that goes from the world frame, the position vector of the n effector frame expressed in the world, which is this one over here, and the position vector of link I plus 1 expressed in the world, right? And we agree that if we take the difference of P of PE with respect to PI plus 1, we get this vector here that we're seeing. This is always to have everything in terms of known quantities that we can obtain through direct kinematics. And then what we also know is that from the expressions that we see in slide 22, that the ones that we derived before, which one? Remember that these were the important ones that were in red circles in a previous slide, where I was talking what we knew and what we didn't. That some depended on the direct kinematics, some depending on the predecessor joints. These are only the contributions of those specific joints. And remember that this expression here, it corresponds the angular velocity from I to I plus 1 is just the derivative of the joint space variable theta I plus 1 are about the axis of rotation of the joint axis, which is set I plus 1. And this is what I'm explaining here. And then we end up with these expressions. Remember, again, we want to have Q dot and the element of the Jacobian matrix, and then I'm just replacing this what we're seeing here, and what we see here is that this qi plus 1 is actually equivalent to the joint space variable, which is this one, and our Jacobian becomes this vector right here, which is the cross product of the axis of rotation set I plus 1 and this vector, this position vector over here. Okay, is this clear? Okay, good. And I'm putting a beautiful square there just to say that that's important. Okay, good. So now let's talk about the angular contribution of the and something that you need to see here is that PE and PI plus 1, they are no longer constants. So this is why we write J of Q, because J depends on the joint space variables, and these are depending on on the direct kinematics. The positions, they depend on the direct kinematics. Remember that we mentioned that we need to know the kinematics of the entire kinematic chain just to find these two. Okay, so the angular velocity contribution. So let's start with the prismatic joint. And then we have the angular velocity of a given link, as we defined it in the previous slides, which is the angular velocity of the predecessor link and the angular velocity contribution from I to I plus 1. Okay. So we can use this expression to find the angular velocity of the n effector just by replacing. So if n is the number of links that we have, actually we can just do the sum, because this is very straightforward, because for angular velocities you just continuously add, because you can just add from the very beginning of the kinematic chain. You can just add the angular velocity contributions here. Basically, this expression here translates to this, because we're just continuously adding just the angular velocities along the kinematic chain. And what we end up with, I mean, if we just this expression, we equate it with what we wanted to find, which is, let's remove the I plus 1 just to make it clearer, just qi dot. And if we want to have this, we just have the sum of the angular contribution. So we just want to make this equal to this, but we still don't know what is the actual value of JOI, right? So let's talk about, in the case of a prismatic joint, as we saw, there's no rotation. So the contribution in that specific for that specific type of joint is 0. This is in slide 21, and leads us to this one. So the vector is actually this. Okay. I forgot this 0 is not bold. Here it should be bold, but a bold 0 means a 0 vector. Okay. And then this is the expression that we care. Now, in the case of a revolute joint, let's start from the same expression as before, which is basically the sum of the previous contributions. So again, we do the same analysis as before. We just add the contributions of all the joints. But now, in the case of a revolute joint, this expression, it's actually something, which is our joint space variable, and this is in slide 22, which is our joint space variable multiplied by the angular, so by the axis of rotation along the joint. So if we draw it like here, maybe I should make a bit of a larger difference. Okay, so this is our joint axis. Joint I plus 1, and this here, sorry about the colors, this is our link axis, right? And this rotate with an angle of theta I plus 1. So what we're getting here is just the theta I plus 1 dot about the axis of rotation of joint I plus 1, which is coming out of the slide. Okay. Let's get rid of this. And this is what I'm saying here. I plus 1 is just the derivative of the joint space coordinates. So this is qi plus 1. And this leads to these expressions, as we did before. Remember that we want to find JOI multiplied by the derivative of the joint space variable, and then we make it equal to our joint space variable, which in this case is theta I plus 1, about the axis of rotation. So what we find out is that JOI plus 1 becomes set I plus 1, which is in this case just 0, 0, 1. Okay, good. Okay, so let's continue. So just to give a summary, now in the Jacobian here, I'm removing the I+1. I just kept it just to be coherent with the previous slides. But of course, let me go back one slide. If we have I+1 here and I+1 on the other side, it means that it's so we have I+1 here on this side and I+1 on this side. It's the same for I and I, and for I. So let's just keep it as simple. So it's already notationally heavy. So let's just remove the +1, and these are the expressions for the Jacobian. If in the case of if it is prismatic, you get just set I and a vector of zeros for the set I for the linear contribution, and a vector of 0 for the angular velocity contribution. And in the case of the revolute joint, you get this cross product of the axis of rotation of the joint axis cross the vector that tells you the position from joint I to the end effector. If it's revolute, and in the angular contribution, it's just basically the axis of rotation. Now it's important to note that set I and the position vector I with respect to the world, they're only a function of the direct kinematics. So this means that they're only a function of Q actually. So this is a very important fact. So we're gonna be using this. So, but first, let's start with how are we doing?
Remember how to compute the ZI? I mean, from the homogeneous transforms composition, you get to the joint frame that you want, you're interested to, and you get the rotation matrix, and you can get the ZI from the third column of the rotation matrix. So the homogeneous transform is, you know, the composition of the homogeneous transforms with.
I'm going to do an example of 2R.
Okay,
so that's I'm going to
fine.
do the direct kinematics, and then I'm going to derive the Jacobian from the direct kinematics. So just don't be worried if you don't get it like this. The example is pretty simple. What time is it?
6:37.
Okay, good. Okay, so the Jacobian that we just derived, it gives us the relations of the linear and angular velocities of the n effector and the joint variables in a specific frame, which is the inertial frame, which is also the world frame. And now let's consider that we want to do a frame change. Okay, so if we want to express the linear and angular velocity on a frame that I'm calling U now, we would have to multiply both the linear velocity vector and the angular velocity vector by a rotation matrix that takes us from the world frame to this U frame. Okay, and this is basically this here, and what we get is that basically the if you want to transform the Jacobian itself, you only need to multiply the Jacobian by this transformation matrix that I'm showing in the slide. Okay, it's just an easy fact. Let's say sometimes you require to do a computation with respect to a different frame of just the Jacobian, you can just use this expression. So let's go to the example of the 2R planar arm. So first, what we do, I'm gonna derive the direct kinematics, and then from there I'm gonna get the Jacobian. So first we define the frames. So frame 0, it's just the base, so it's fixed, it's not moving. Then we define frame 1 as the frame that supports link 1, which is this one that I'm showing in the slide. Then frame 2, it's the frame that supports link 2, and then we have the end effector frame, which is this one here. Then we want to define our joint variables. So Q1, we define it as the angle between frame 0 and frame 1, denoted here in red with in the slide, which is Q1. Then there's the length of this is not a joint variable. This is just the length of link 1, which is going to be useful to compute the Jacobian. Q2 then it's the angle between frame 1 and frame 2. And then we have the length of link 2. Actually, this length should be all the way to the end effector. But I thought it looked a bit ugly, but this length is actually to the end effector frame. Because then you would have to have another length here, and then it becomes a mess. So I'm just keeping it like this just for visualization, but it's supposed to go all the way to the end effector frame. So let's start from frame 0 to frame 1, and we have a pure rotation here, denoted here. So the pure rotation of this, it's how do we compute the pure rotation? So if we want to get the transformation matrix of a pure rotation, how do we get it? This is along the z axis. So do you remember?
Rotation matrix along the z-axis.
So tell me the term. So just tell me the terms. Cos.
And then all the zeros.
Okay, yeah, that's it. So we have the rotation matrix along the z-axis, and then we have the cosine of q1 minus the sine of q1. So this is just basically the rotation matrix along the z-axis is a pure rotation. Okay, then let's see about from 1 to 2. So it's a roto translation. So we have, I'm going to put here what we already know, which is the bottom row of the slide of the matrix, and we have a rotation of q2 from the joint axis of the predecessor link, which is 1 to the link that we care. So it's just basically a rotation about the z-axis, right? Remember that we're doing from 1 to 2. So it's just basically a pure rotation. Well, this is a rotation around the z-axis. And then for the translation, there's no joint, there's no prismatic joint. So it's basically a constant translation, which is just the length of the link. And our column becomes this. So this is just the transformation matrix from 1 to 2. Then we want to see from 2 to E, there are no joints in between 2 and the end effector. So it's just a rigid transform represented by the distance. Now I put the L2 all the way to the end effector. So it's just basically having an identity matrix for the rotation, because there are no rotations, and just for the translation, we just put L2. Now we want to obtain from 0 to 2 first. So we want to do the composition of homogeneous transformation matrices, which is multiplying from 0 to 1 and then from 1 to 2. And we get this. I'm not going to work out of all of the products, but this is what we get. Remember, you're going to get cosine 1 times cosine 2 plus sine 1, sine 2. And then from here, we use our trigonometric identities. And you end up with this q1 plus q2 inside of the cosine and sines. And if you do the multiplications, then you end up with this. Now let's, it's important, I wanna highlight this term here, because this is actually telling us the position of link, of the frame of link 2 with respect to 0, which is our fixed frame. And we're gonna use it in the final slide when we're thinking about the Jacobian. So that's why I'm highlighting it here. Now let's do all the kinematic chain, which is a very simple one. We only have 2 degrees of freedom. So from the 0 to the n effector is just basically taking what we already did and multiply it by the rigid homogeneous transform to the n effector, and we end up with this. And again, we use our trigonometric identities. If you work out the matrix multiplications for yourself, you find out that you get this. And again, this is also important. This is telling us the position of the end effector link frame with respect to frame 0. So now let's get to the Jacobian. Remember that we want to find the linear and angular velocities expressed as a function of the joint velocities. In our case, the dimension of J it's going to be 6 by 2, because remember that we're working on Cartesian workspace, so we have three linear velocities and three angular velocities. That's 6 that go here. We have our 6 dimension, and then we only have 2 joint variables. So here we have 2, because we only have 2 degrees of freedom in our actuator, in our manipulator. Sorry. Again, we have J1 and J2. We can decompose the Jacobian into our two columns of the Jacobian, which is J1 and J2. Remember that Ji it's of it's a six-dimensional vector. And for a revolute joint, we have 2 revolute joints. Remember, this is the expression that we derive for the Jacobian. Remember that this is on top we have JPI. Well, I'm gonna write this y equal, and on bottom we have JOI. Okay. Okay. So we're gonna be using this expression to derive the Jacobian. So in the end, when you're talking about when you're doing the geometric Jacobian, the only thing that you need to know is the type of joint that you're dealing with. Then you just refer back to the expression, and then it's very simple to derive this matrix. Of course, the more degrees of freedom your manipulator has, your robot has, then it starts becoming very complex. For example, in our robot, the foot Jacobian, because we want to compute the position of the feet, it's not super straightforward to just derive it by hand. So we use a library that does it for us. In our case, we're using RobCogen, but there are many. There's Pinocchio, there's RBDL that do this for you, and they are especially useful when you have many degrees of freedom and many redundancies, because then those libraries, they use numerical inverse kinematics and numerical methods to derive all of the complex expressions that are related to the redundancies. But in any case, let's go back to this. So in our case, first let's start with the first column. So if we want to obtain for joint one for our joint for our link 1, we have the axis of rotation of link 1, which is set 1, multiplied by the position vector, by the difference of the position vector of the end effector minus the position vector to link 1, and then at the bottom we only have the axis of rotation of the joint. Remember that this axis of rotation of the joint is the axis coming out of the page, this set 1 coming out of the page. And then for link 2, we just have the axis of rotation of link 2, which is here coming out of the slide, and then we have the difference of the end effector minus the position of the end effector minus the position of link 2. Okay, and then the axis of rotation Z2. Now this is actually 0 PE. Oh, this is a mistake actually, because because this is actually the position vector from 0 to 1. They are on top of each other, so there's no difference in between them. So this actually is 0. This is 0 PE, which we obtained from our homogeneous transformation matrix that I showed you before, the one that I highlighted. And this is 0 P to E. So it's basically the position vector from link 2 to the end effector. And we don't have this yet, but we can obtain it. So this is basically this difference here. Remember that we already have the position vector of the end effector. And this one we get from the homogeneous transformation matrix from 0 to 2. And which we derived before. So if we put the expressions of 0 PE, we get this. I'm just taking this from the previous slides, and I'm using the compact notation of cosines and sines. And this is also the position vector that we have here. And this is what comes out of this operation right here. Okay. Now, if we replace all of what we see, like the end effect, the position of the end effector, the position of the vector of position from 2 to the end effector, and the axis of rotations of joint I and joint 2, what we're going to get in our expression from the Jacobian, what we're going to get is basically this. Now, remember that here, there's a cross product. So this is why you see minus sign. This is why you see, but there's the cross product. If we go back one slide, I'm just doing this cross product right here. So I'm just doing the cross product of the end effector, sorry, of the axis of rotation 001 cross the position of the end effector. And this is what you get for the geometric Jacobian of the 2R planar arm. And basically, in the end, this is what we're going to use for, oh, this is not Q. This is, oh my God. It's going to be JQ times this. Okay. And this is going to give us the expression for the linear and angular velocities.
Do you have another exercise? We do a short break of 5 minutes.
For now, I don't have another exercise. I mean, I have another exercise, but only related to the analytical Jacobian.
But how many slides do you use?
Now 41, so we have.
I think it's good if you do a break. Like, are you tired? Do you see your concentration is dropping, or?
Yeah, it's good that we do a break now. Let me finish just with some comments,
yeah,
and then just related to Jacobian,
yeah,
and then the next when we come back, we start with the analytical Jacobian. Okay, so just some comments related to the exercise that we just did. So the dimension of the Jacobian, as I mentioned, it's going to be 6×2. So what we're doing basically is that we're mapping from the joint space, which is of dimension 2, to the Cartesian workspace, which is of dimension 6. And what's helping us to do this mapping is this Jacobian, the geometric Jacobian matrix. And in general, the dimension of the Jacobian is 6/n, where 6 corresponds to the Cartesian workspace variables, which are 3 linear Cartesian workspace variable and triangular Cartesian workspace variables, and n, it's the number of joints of joint space coordinates that we have. So in the case of this simple exercise that we did, it's 2. And what we're doing is just mapping, again, from joint space to Cartesian workspace. But the most important takeaway from this is that the maximum number of linear and angular end effector velocities that we can assign independently depends on the number of joint space variables that we have. And this is going to become clearer when we do the comparison between the analytical Jacobian and the geometric Jacobian. But this is just for you to keep in mind that we can only assign if you only have two degrees of freedom, you can only assign independently to end effector velocities. So for example, we cannot assign simultaneously. In this case, we cannot assign the velocity of x, the velocity of y, and the rotation rate of the end effector. We can only assign 2 of them at the same time because we only have 2 joint space variables. Okay, so if there are no questions, we can take a break now. 15 minutes. So 10 minutes.
And then you finish a little bit earlier.
Okay, so we take a 10 minutes break. Now it's 8:53. We come back, well, 54 now. We come back at 7:54 and we finish 15 minutes earlier. Or...
Well, you finish the analytic Jacobian and that's it.
Okay, good. So we come back at...
Good to conclude the argument.
Okay, 7:54. Mute. Aspetta un attimo che devo Okay, can you hear me online? Sorry for the delay. There was a question in the break. Can you hear me properly? Okay, good. I see that somebody already replied. So let's continue.
The example, what velocity of the energy related to the X component of the Y?
Sorry?
The example, what the linear velocity of the n factor? Which one? But like the X component, the component of
I don't understand the question. You're
Which one you calculated?
yeah, what is the
E is the end effector. It's all of them. So it's V is it's a three-dimensional vector. So it's the X, Y, Z, omega. It's around the vector. It's around the vector omega. So it's both are three-dimensional vectors. Okay. Yeah, that's why the mapping goes from Rn to R6, because you're mapping from the joint space variables to the Cartesian space variables, which is 6. I think you're a bit confused about the task space, because task space we have only 3. Okay, good.
We see next to the analytic Jacobian that you don't have to have 6 variables in the task space, but you can have it less or define your own variables. The geometric Jacobian, you can do only that.
Okay, so let's go to the start of the analytical Jacobian. So let's start with an initial question, which is, why didn't we just differentiate the direct kinematics? So basically, why didn't we just get the derivative of f of q, and that's it? And that's actually something that we could do. And now I'm here expressing the direct kinematics also as a vector, which is a vector of position, and this which represents position, and also this is also a vector, but it's important to know that this phi, it's also a vector, but remember that this is not part of a vector space. So it's just an array of angles. This is what I am mentioning here. This is just a set of Euler angles in our specific case. So we can obtain the derivative of r with respect to time using the chain rule, as we showed before. And what we find here is that we get this partial derivative of the direct kinematic functions with respect to the joint space variables multiplied by the derivative of the joint space variables. And this is what we call the analytical Jacobian, which is, and it's basically represented by this capital J, R. R is related to the task space, and it's always as a function of the joint space variables. So let's see how we can get the analytical Jacobian. So we just remember that the function of that describes the direct kinematics, it's a multivariable vector valued function. So f of q, it's actually a vector that depends on multiple variables. So q, it's also, I mean, can be arranged as a vector, but q, it's basically q1, there's q1, q2, qt, which are the joint space variables. So the dimension of q depends on the number of task space coordinates, what we were just mentioning before, that you can select the number of task space variables that you're interested in, which could be position in x, position in y, position in z, the orientation that you want, Euler orientations. So for example, in the case of the 2R planar robot, the size of the task space, it's of dimension 3. And in this case is related to the position in x, the position in y, and the angular on phi. So this we'll see in the next slide. And this is the way. So if you take the derivative of the previous expression, where is the? Do you know where did I leave there? Okay. If you take the derivative of the direct kinematics expression, which is this f of q, now you need to know that you don't get a vector, you get a matrix, because you need to do the partial derivative of each of the rows of the vector with respect to each of the joint space variables. So for example, the top row, you have the first row of the direct kinematics function with respect to Q1. In the second one, you have it with respect to Q2, and so on and so forth to Qn. Qn, remember, it's the number of joint space variables. And then if you go all the way to the end of this vector, remember M, as we defined it in previous lectures, M is the number of task space variables. So that's why this matrix ends in N on the columns and has M rows. And then we go the way to the end. So the M row of the direct kinematics function derived with respect to all of the joint space variables here. Okay, so this is a very straightforward way to obtain a relationship for the velocities in the task space. So let's see how can we get the analytical Jacobian with our old friend, the 2-hour planar robot. So here I'm just showing already the direct kinematics function, which you can obtain both from the direct kinematics that I worked out in the previous part of the lecture, and also you can get them by geometrical relationships, because this is a pretty straightforward example. So if we differentiate with respect to time each of this, we get the following, which is basically, remember that whenever you derive a function with respect to time, you need to multiply with respect to the variable itself, the derivative of the variable with respect to time. And this goes also in the case of this one. That's why we get Q1 dot, Q2 dot here. And it's the same case for the joint space variable in Y. So actually from here, you see that Q1, Q2, Q2 dot, Q1 dot, Q2 dot, and here Q1 dot. They're actually you can actually organize them in a vector very easily, and you get a very nice matrix multiplication because they are not included inside of the sine and the cosines. So in the end, we can rearrange this in this way, and this is actually Q dot. And what we end up with in the matrix that we see on the right hand side of the equation, it's actually the analytical Jacobian. And of course, you cannot do this for every robot that you have, because you cannot always have a geometric intuition of the direct kinematics, and you cannot get like nice expressions that you can derive. So also sometimes the derivative of the direct kinematics is not so straightforward. So or let's say of a specific row. But this is a nice example. But let's find another way to do it, which is based on the matrix that I showed at the end of the slide, where I explained the analytical Jacobian. So we can do the same thing as we did before with the direct kinematics, but let's rearrange it as a vector, right? So if we take if we just plug in this direct kinematics function into our formula for the analytical Jacobian, what we're gonna get in the end, it's the same thing as we got before. Okay, and this is the analytical Jacobian. Let's see. So let's do some comments, and maybe with this we can finish the lecture, and then in the next lecture I'll finish with some relation between the analytical Jacobian and the geometric Jacobian. So the analytical Jacobian, in the case of the 2-hour robot, is of dimension 3 by 2. And this allows us to do a mapping from the joint space, which is, as we said, that we have 2 degrees of freedom, it's 2, to the task space, which is of dimension 3. So in general, the dimension of the analytical Jacobian is m by n, where m corresponds to the number of task space variables, and it does this mapping. There's a comment in the chat. Okay, that was the one saying that they could hear me. And then we do this mapping, which takes us to the joint space, to the we get the velocities from the joint space map onto the velocities of the task space. And I would say this is my last slide for the day. Are there any questions about this? If not, then we'll see each other tomorrow. Okay.
Just a comment on the analytic Jacobian. You need a symbolic expression to compute it. And whatever we have available from the market are libraries that usually does this computation numerically, like we saw for the homogeneous transforms. So this is one of the issues in doing this symbolic computation for a big number of degrees of freedom. It becomes easily untractable. So that's one of the issues. We introduced the reason for which we introduced the geometric Jacobian, because geometric Jacobian you can always compute.
Okay. Good.
A talk made by myself at Aquario di Genova. It will be online, I think, tomorrow.
Yeah, that's a good.
Wednesday, and I can give you the link. It's in Italian. I'll give you just a big introduction on our work on quadrupeds and some results with a project with Inail, where we teleoperate a Centaur robot, and we collect objects, open doors, and teleoperation from a remote room that with virtual reality. It's quite interesting. I can, if you're interested, I can put even the link.
We can send an announcement.
We can send an announcement.
Yeah.
Okay.